we are at the last subtopic of this chapter, that is charge in a uniform electric field. In this subtopic, I will explain quantitatively with the aid of a diagram the motion of charge in a uniform electric field. And for this uniform electric field, we have a specific equation for the electric field strength. We are going to look at the motion for these four cases. We have motion of stationary charge in between two plates, charge moving perpendicular to the field, charge moving parallel to the field, and charge in dynamic equilibrium. Uniform electric field is special. Why? Because it is only formed in between two plates of opposite sign. So we have plus and negative. So the direction of electric field is always from positive to negative, and the uniform electric field is represented by a set of electric field lines which are straight, parallel to each other, and equally spaced, meaning the distance between the two lines are the same. So itu maksud equally spaced. The equation for uniform electric field is given by the electric potential divided by the distance between these two plates D. So electric potential here is actually the change in potential, since in this case our change in potential is V minus 0, so it is equal to V. Charge in uniform electric field, we have few cases. So this is the first situation, that is stationary charge. Stationary charge is said to be at static equilibrium. So for this condition, the electrostatic force that is acted towards the positive charge, because this is negative, is having the same magnitude with the weight of this charge, but it is acted in different direction or opposite direction. So because of this, it is not moving or stationary. The second case is the charge moving perpendicularly to the field. So we use electron for example. So this electron has mass me and initial velocity u. Okay, what happens here is when this charge is entering the region of uniform electric field, this negative charge will tend to attract to positive charge. Because of the upward electric force, it tends to move to the upward. It will cause the electron to move along the parabolic path. So here is the motion of the electron in the uniform electric field when it is entering perpendicularly to the field. And this is the trace of the path. So this path is called as parabolic path. The parabolic path is always under the influence of acceleration that is coming from the electrostatic force acted on the electron. So that is electrostatic force with equation QE, and QE is equal to MA, the basic equation of force in motion. So here A is equal to Q over M times the electric field strength. So this acceleration is always acted for vertical motion. And again, if this is a parabolic path, you can recall chapter 2 in the previous semester, semester 1, we learned about projectile motion. So in projectile motion, we have a few terms for x and y axis. We have a few equations. So please recall what you have learned, and you are going to apply this equation for the case of charge moving perpendicularly to the electric field. So AY here for the y-axis is equal to this term of acceleration. Now we look at the third case or the third situation, that is the charge moving parallel to the field. So in this case, we have a charge in between the two plates, positive and negative. So when the charge, let's say we have positive charge, so it will tend to attract to negatively plate, so the motion is downward. And if we have negative charge, it will tend to positively plate, so the motion of charge is upward. So when every charge is moving, it will have its own acceleration. Let's say we have the other case. We have upward direction of electric field and we have positive charge. So this positive charge will move upward because it tends to attract to negatively plate. And if we have another example of negative charge, so it will tend to attract to positively plate. So based on the motion previously explained, we have the motion of charge is because of the attraction in the electric field, so it possessed electrostatic force that is equal to QE, and because of the motion, the electrostatic force is equal to MA. So we equate the two terms, and finally we can use the term A for the acceleration, that is equal to Q over M times electric field. Q is the magnitude of charge. We can also apply these three kinematic equations to find the velocity, initial velocity, and time, and also displacement for the charge that is moving parallel to the field, as explained just now. Here comes the last case of charge in uniform electric field. So this is the case or the situation for charge in dynamic equilibrium. So for dynamic equilibrium, again we have the electrostatic force that is acted upward and weight acted downward. Both of these forces are having the same magnitude, but it is acting in opposite direction. So the charge will move at constant speed because both will be attracting in opposite direction, and the charge is said to be in dynamic equilibrium. And this is the motion of charge when it is in dynamic equilibrium. So the difference between static equilibrium, as discussed in the first situation, static equilibrium is just about the same with dynamic equilibrium. The static equilibrium, but for static equilibrium, the charge will not move. It is stationary. Okay class, before we stop, last but not least, we do the chapter summary for the whole chapter. So quickly we have, for this chapter, we have 4 basic quantity. We have electrostatic force, we have electric field, we have electric potential, and electric potential energy. And this is the, okay, these first 2 quantities are vector quantity. So you have to consider the direction. You have to draw the direction for both quantities. And for calculation, you are not considering the sign of charge. You not include the sign of charge. But for these 2 quantities, it is a scalar quantities. But for these 2 quantities, they are scalar quantities, meaning it has no direction, and you have to include the sign of charge in calculation. And then we have, in the last subtopic, we have the charge in uniform electric field. Okay, uniform electric field. So for this electric field, we have a special equation that is the change in potential divided by the distance between the 2 plates. Okay, so we have a few situations for the charge in between 2 plates of positive and negatively plate. So the direction of electric field is going to be from positive to negative. Okay, so the first case, we have the static equilibrium of the charge. So the charge is in equilibrium with the weight, and also the electrostatic force if we have negative charge here. And then we have the second situation is we have the charge that is coming perpendicularly entering the electric field region, uniform electric field. So what happened here is this charge will deflect is either to the lower plate or to the upper plate. It depends on the sign of charge. Okay, and the third situation is when the charge is moving parallel to the electric field. It's either upward or downward. It depends on the charge, on the sign of charge. And lastly, we have the charge in dynamic equilibrium. So for dynamic equilibrium, it is again in equilibrium. So you have electrostatic force is balanced with the weight, but this time it is moving with constant velocity in a straight line. So that's all for the chapter summary. Alright, finally we're done chapter 1, electrostatics. Hope it is very helpful for you. Thank you very much.